Awesome. Yeah. Hi, I'm James Logan. I'm an engineer. I did my training in mechanical engineering out here at MIT. Went from there to 5 years doing engine development on the M1D and Raptor engine programs at SpaceX. Spent about 5 years there, and then I've been at Commonwealth Fusion Systems as a scientific software engineer, mostly doing electromagnetics for fusion power and superconducting magnets for the last 5 years. And what you're going to see here is my longtime hobby turned side project, Deimos, which is my attempt to sort of move the needle on the quality of data acquisition for mid-speed experimental systems. So I've been working with data acquisition systems at a hobby level for about 15 years and professionally for the last 12 years. So I've seen a lot of the ways that people do these things now, and a lot of ways to not do exactly what I'm trying to do. Data acquisition systems, you can certainly get them now. They span from the interface with an experiment where you have analog signals coming from sensors back to send the data in digital form back to a server, and then usually onto a database from there. And then they usually also include some capability to output control signals to the experiment as well, to turn things on and off and up and down in an experiment. So you can definitely buy these things now. They exist. They have existed for a long time. They're actually what Ethernet was developed for, but they are expensive, and they often don't have the level of documentation that is needed for reproducible scientific work, or they just don't do exactly what one would hope. So the goal here is to hit a price point that's at or somewhat below the price point of the existing mid-range stuff, while targeting the data quality and usability of the high-end stuff. It's definitely possible. It does involve sort of moving on from the status quo in a lot of ways, particularly avoiding calibrations for individual units by using precision components that you just need to test, and avoiding per unit configuration and expensive subscriptions and platform restrictions. So if you've had text from a vendor on site adding, yet more clock hardware to your system so you can get time synchronization for your data acquisition stuff that already costs more than the lab that it's in, or stuff like that, then this is for you. So there is hardware associated with it. I'm not going to spend too long on the hardware because this is a software talk, but it is also 100% open source. And includes integrated analog front ends for a variety of different sensors, which is another important aspect of maintaining good signal quality and low cost. And the microcontroller that samples the data from the hardware also runs 100% bare metal rest. So that's no operating system and no allocator. And you can also program your own firmware on it if you want to. It can be programmed either using a REST API, which is the nominal API. The whole control program is written in REST as well. Or there will also be Python bindings, and there's a node graph style graphical interface that is in work as well. There are kind of two major aspects to data quality when you're sampling data. And one is time synchronization, both between multiple modules that are measuring and controlling different parts of the same experiment, and jitter in timing for a given module. And then we'll also talk about filtering and signal processing as well. But for time synchronization, the system is able to maintain sub-microsecond time synchronization between multiple units in the same system entirely in software. So there's no need for expensive and complicated PTP systems. Those still have some application to things that go into the nanosecond and picosecond regimes, but I'll leave that to the particle accelerator folks. For signal processing, it has sort of a typical architecture, I think, for digital filtering, but somewhat different from what people would usually put in an embedded system like this. There's a digital Butterworth filter running on the microcontroller for each channel, and that is actually initialized and constructed on the microcontroller, which is a little bit odd. So it's sort of like the minimum form of adaptivity and filtering is to just adapt to a choice of sample rate, which normally involves a fairly complicated process to construct the filter coefficients. But we'll look at how that's done without any real computing resources available. And then every digital filter needs an analog filter in front of it. Digital filters can only operate on signals below their Nyquist frequency, and to filter things above that Nyquist frequency, you always need an analog filter of some kind in front of that. So this is the combined effect of the digital and analog filters that are on every channel. So that's the ADC input filter and the digital filters running inside the microcontroller. And then there's also a layer of filters in each analog front end. But you can see there's a sort of a trade-off to be had in terms of controlling the phase lag at the Nyquist frequency of the reporting rate, which is also the control rate if you're sending commands back and forth to the experiment, and limiting the amount of aliasing from frequencies above the reporting rate. So kind of is organized to strike a balance between those two, so you can both get good data and also good quality controls. And this is accomplished using flaw, which is a library for doing digital filtering on embedded systems with no operating system. So starting from the state space form of a infinite impulse response filter, you kind of have a matrix form. But on inspection, there's only one non-trivial row in the matrix. So instead of doing a matrix multiplication at each state update, you can actually boil it down to a couple of vector dot products and shifting a ring buffer. And you can store the entries in the non-trivial entries in those matrices in tables, and interpolate on them at runtime to construct the filters live and quickly, so that you can make the filter that you need when you need it, without the full huge system of linear algebra and math that goes into building these in the first place. And then you can also do some tricks in terms of how you organize the state update to make the floating point error work with 32-bit floats, which is a fairly delicate operation. And then there's also a step of error correction done to correct the steady state gain of the filter, both for floating point error with 32-bit floats and for the little bit of error that's introduced from not producing perfect values out of an interpolation. In flaw right now, and soon to be on the hardware as well, there's also going to be a fractional delay filter for each channel running alongside the digital Butterworth. And the purpose of that is going to be to take the sampling, where you can see these individual vertical black lines here are groups of channels that are sampled simultaneously with each other, but they can't all be sampled at the same time because there are 20 channels and only 3 ADCs. And so there's like this sort of burst scanning pattern. And a fractional delay filter allows you to effectively produce a fixed time delay in a filter using a signal processing trick. And that allows you to individually tune groups of channels to effectively make them appear to be sampled simultaneously. And so you get the effect of simultaneous sampling in your data quality without the massive expense of purchasing truly simultaneous sampling analog to digital converters. Constructing the filters live is done using interpn, which is a system for doing multi-dimensional interpolation with also no standard library and no allocator. So for bare metal applications, and this is done using the recursive strategy for evaluating an interpolation. So you can do interpolation on one dimension at a time until you get to your final interpolated point. And if you diagram it out, the information dependencies in the system form a tree, and you can traverse that tree depth first, so that you only ever have to actualize data that scales linearly with the number of dimensions instead of exponentially with the number of dimensions. And you'd think that throwing away the tool of allocation would come at a cost to performance. It certainly doesn't vectorize very much. But it turns out that it actually is remarkably fast and is even comparable to the best stuff for specialized low dimensional interpolators, and somewhat faster than the more general high dimensional interpolator methods that are available right now. And also produces somewhat better floating point error and quality of fit in a lot of cases. So yeah, to summarize, the future of data acquisition is in Rust, both for performance and reliability reasons. And we can definitely do better than the status quo. And it turns out it's not actually particularly hard and doesn't require any particular novelties to achieve that.
Thank you. That was really interesting. So once again, if anyone has any questions, type those into the Q&A box, and then James will be able to answer those. I'm not saying anything yet, but I'm sure people are busy typing. I have a question for you quickly.
Yeah.
Most of my own curiosity. So on Wednesday, we had a talk about the interpn crate, and you were talking about the ninterp crate. Are those
this is interpret, and I think the one that you guys had earlier in the week is like ninterp or interpnd or something. And yeah, I need to take a look at that. I just got done traveling, but I need to actually go watch the talk for that. But that is based on the ND array backend, and so that is going to require allocation in the standard library.
Okay, so they're targeting a slightly different problem. So that maybe do you need both this? Yeah, I was sort of wondering if you and Kyle, it looks like, who was talking on Wednesday, should talk to each other and see if it's something you could work on together.
Yeah, we definitely should. Yeah, I think this can. I haven't generalized the strategy for interpolation that much. I've only written the linear and cubic methods, and haven't sort of done the legwork to extend it to arbitrary polynomial order, stuff like that. But yeah, I think it could be, and I think having a good API that interfaces with NDRA in an ergonomic way, combined with that kind of evaluation pattern, could probably be pretty powerful.
Yeah, so we had a question come in on the Q&A box. Rito asks, which MCU are you using for the hardware?
That is a STM32H743. So it's running at 400 megahertz, and it is a pretty powerful microcontroller. It's sort of just short of the crossover microprocessor range, and I run it with just the internal flash and RAM. So there's no external stuff for it at all, except for an Ethernet PHY.